Have you ever wondered what infinity really is? What does it mean for something to be infinite? It's a concept that has been around for thousands of years, captivating the minds of people from ancient civilizations to modern mathematicians. The idea of infinity, of something without end, is more than just a philosophical musing. It's a key aspect of many mathematical theories and real-life situations. Historically, infinity was a concept shrouded in mystery and even fear. Ancient civilizations grappled with the idea, trying to understand the boundless nature of the universe. Fast forward to today, and infinity is at the heart of numerous mathematical disciplines, from calculus to set theory. It's a concept that's both abstract and incredibly practical. It helps us calculate limits, understand geometric patterns, and even unravel the mysteries of the universe. So, buckle up as we embark on a journey into the fascinating world of infinity and set theory. Enter Georg Cantor, a mathematician who dared to tackle infinity head-on. Georg Cantor was a mathematician with a revolutionary idea. He wasn't just content with accepting the concept of infinity as a vague, all-encompassing figure. No, Cantor wanted to quantify it, to break it down, to understand it. This drive led to the development of set theory, a cornerstone of modern mathematics. In the world of set theory, things are not always as they seem. A set is simply a collection of distinct objects, like a bag of marbles or a deck of cards. But what happens when you start dealing with infinite sets? That's where things get interesting. Cantor's groundbreaking work on set theory introduced the concept of cardinality, a measure of the size of a set. He demonstrated that even in the realm of infinity, not all infinities are created equal. Some are larger than others. Mind-boggling, isn't it? Consider the set of natural numbers. 1, 2, 3, and so on, extending to infinity. Cantor showed that this set is countably infinite. Now consider the set of all real numbers. This set is uncountably infinite, a larger infinity than the set of natural numbers. Cantor used a method called diagonalization to prove this astonishing fact. His approach was met with resistance and even hostility from some corners of the mathematical community. Yet, it was a pivotal moment in our understanding of infinity. These revolutionary ideas about the existence of different sizes of infinity, represented by the Aleph numbers, have far-reaching implications. They play a crucial role in many areas of mathematics, from number theory to calculus and beyond. Cantor's work was more than just a study of sets. It was a bold exploration into the infinite, a journey into the unknown. His theories challenged previous notions and laid the groundwork for future mathematical discoveries. Cantor's work sparked a new understanding of infinity, opening a world of infinite possibilities. And that, my friends, is the beauty of set theory. The seemingly simple can lead to the profoundly complex and in the process open up a universe of understanding. Imagine a sequence of numbers that never ends. What happens when we try to sum them up? This question introduces us to the concept of an infinite series. An infinite series is just that, a sum of an infinite sequence of numbers. But here's the catch. Can an infinite series ever actually reach a sum? Think about the harmonic series, one of the oldest and most familiar series. It's the sum of the reciprocals of all natural numbers, starting with 1. So it's 1 plus a half, plus a third, plus a fourth, and so on, extending infinitely. Now you might think, if we're adding up an infinite number of numbers, wouldn't the sum be infinite? Well, not necessarily. This is where the concept of limits comes into play. In mathematics, a limit is the value that a function or sequence approaches as the input or index approaches some value. The limit of an infinite series, if it exists, is the real number that the series approaches as the number of terms goes to infinity. Going back to our harmonic series, as we add more and more terms, the sum does increase. But it doesn't just grow uncontrollably. Instead, it grows logarithmically, which means it grows slower the more terms we add. So, does the harmonic series have a limit? The answer is no. The harmonic series is an example of a divergent series, where the sequence of partial sums doesn't approach any finite limit, as the number of terms goes to infinity. But not all infinite series diverge. Some, like the geometric series, do converge to a finite value. In the case of the geometric series, if the common ratio is between -1 and 1, the series converges to a limit. As we can see, infinity often behaves in ways we wouldn't intuitively expect. The concepts of infinite series and limits allow us to grasp the seemingly ungraspable, adding yet another layer to our understanding of the vast and fascinating world of mathematics. But what about the other end of the spectrum? What happens when numbers become infinitely small? These are called infinitesimals, and they're a fundamental part of calculus. Picture this. You're attempting to measure a curve. By its nature, a curve is, well, curvy. It doesn't have straight edges. So if you try to measure it with a straight ruler, you're going to have gaps. Infinitesimals are the mathematical equivalent of a ruler that can bend and flex to fit the curve exactly. They're represented in differentials like dx and dy, and they allow us to make precise calculations about rates of change and areas under curves. But let's shift gears and talk about something that seems counterintuitive. Different sizes of infinity. Yes, you heard it right. In set theory, introduced by Georg Cantor, we have a way of representing these different sizes of infinity using what are known as Aleph numbers. Aleph numbers are denoted by the symbol, followed by a subscript. The simplest of these, 0, represents the cardinality of the set of all natural numbers, which is a countable infinity. But things get wilder from here. Consider the set of all real numbers between 0 and 1. You'd think that since it's constrained between two finite numbers, it should be countable, right? But no, this set is uncountably infinite, and has a greater cardinality than the set of all natural numbers. This larger infinity is represented by 1, and it doesn't stop there. You can keep going, finding larger and larger infinities, all represented by different Aleph numbers. It's a concept that can make your head spin, but it's a fundamental part of understanding the vastness and complexity of the mathematics of infinity. So, infinity isn't just a single concept, it comes in all shapes and sizes. This just goes to show how deep the rabbit hole of mathematics goes and how much there still is to explore and understand. But with infinity, things can get a bit paradoxical. Paradoxes, you see, are situations that defy our intuitive understanding of reality, and when infinity enters the scene, things can get downright bizarre. Let's take a look at one of the most famous paradoxes related to infinity, known as Hilbert's hotel paradox. Imagine a hotel with an infinite number of rooms and suppose that every single room is occupied. Along comes a new guest seeking a room. Our intuition tells us that the hotel is full, right? But since it's an infinite hotel, the manager can shift every guest from room number and to room number and +1, creating an empty room at the front for the newcomer. Despite the hotel being fully occupied before, it can still accommodate an extra guest. Now, let's up the ante. Suppose an infinite bus carrying an infinite number of new guests arrives at the hotel. It seems impossible to accommodate them all, doesn't it? However, the manager has a trick. He moves the guest in room into room 2n, freeing up all the odd-numbered rooms for the new guests. So despite the hotel being fully booked, it can still house an infinite number of extra guests. These scenarios may seem counterintuitive, but they are logical outcomes when we deal with infinity. It shakes up our usual understanding of numbers and space, challenging us to expand our thinking. Infinity, as we've seen, is a complex and fascinating concept. It challenges our understanding of the world, and continues to perplex mathematicians to this day. But isn't that what makes it so intriguing? Understanding infinity isn't about reaching a destination, but about the journey of discovery, the exploration of the endless, the pursuit of the unfathomable. And in that pursuit, we continue to unravel the beautiful complexities of the mathematical universe. So, there you have it. A peek into the infinite world of set theory. We've journeyed from the foundational work of Georg Cantor, through the awe-inspiring concept of infinite series and limits, and into the realm of infinitesimals and Aleph numbers. We've grappled with the intriguing complexities of infinite metric spaces and the enchanting symmetries of fractal geometry. We've dipped our toes into the vast ocean of infinitesimal calculus and the intricate lattice of infinite number theory. And of course, we've glimpsed the paradoxical wonders that infinity can conjure. This voyage into infinity is just the beginning. There's so much more to explore, to question, and to understand. Whether it's diving deeper into the mysteries of set theory or venturing into new mathematical territories, the journey is sure to be as boundless as the concepts we've discussed. Remember, with infinity, the possibilities are, well, infinite. Until next time, keep questioning, keep exploring, and keep marveling at the wonders of mathematics.